Thank you for the nice introduction. Hi, I'm Madhu, and I would like to start with thanking Professor Skopil and Professor Kim for inviting me to give a presentation at Sequest seminar. Would also like to thank Professor Lee for taking out the time and having discussion with me. With that, I'd like to start the presentation. So, as the title suggests, I will be talking about cosmology in string theory, a new paradigm. Although researchers have been looking at this subject for over 2 decades, it seems like that we have only scratched the surface. And as a relatively new, this is relatively new area for me. So every day I find something exciting and something new, and I'm very eager to explore this more. That is why I'm also excited to have the opportunity to present here so that I get your uh, expert opinions. I don't know. I'm not able to change my slide.
Are you using this?
Yeah. Should I do this?
Uh, do you have any? That's right. Yeah, you can move from this using these arrows.
Okay, and this one is for the point. Okay. All right. Okay. So as I see it, there are two successful spectrum. One is theoretical spectrum, where the superstring theory is considered as best candidate for quantum gravity. And as a observational spectrum side, we have successful inflation models where we can find specific values to these key parameters in cosmology, which are scalar to tensor ratio or spectral index, and we can constrain them from cosmology values which you get from CMB observation. So I started with constructing high derivative action in supergravity, hoping that it would be useful in black hole physics or maybe in other phenomenology projects. But it turns out that it's very difficult to use any of the construction that I did. So now I'm moving towards inflation model and trying to see this in inflation model in supergravity background. So I am somewhere, this is not changed. Have I been disconnected because I'm not able to change something?
We lost connection.
Paused. I don't know what is happening. This is the Zoom.
Yeah.
Do I need to sign in?
Login again to this one.
We're sharing it again.
You try to do that contacts. Exactly. Yeah, nice.
So I'm somewhere here. So I'm moving little away from string theory and going more towards inflation theory, but still trying to use the supergravity construction that I did. So this is where I am. And so let me start with some motivation, although I know everyone knows the motivation, but just for the sake of completeness. So we have three forces in small scale, which are electromagnetism, weak nuclear force, and strong force. They all can be described within quantum field theory. And then we have large scale force, which is gravitational force, which can be described within general relativity. However, when we try to combine these two forces, which means we want a theory that can describe gravity in small scale, we end up with infinite number of counter terms saying that we have a theory which is non-renormalizable. But what's the problem? We could be happy with two successful theories, However, our universe acts as a snake that bites its own tail. So basically, this goes by the name cosmic Ouroboros, which gives you a link between macrophysics and microphysics. So this diagram has a lot of information. So basically, here are we, the mankind, and if you move towards your right, you successively get larger and larger scale. So you have mountains, planets, your solar system, and then your universe. And if you move towards your left, you end up with smaller and smaller scale, starting with ants, amoeba, DNA, atoms, nucleus, and then some of the particles that are predicted by some particle physics. Okay, so this tail is like a big bang point where you cannot get rid of larger scale or small scale. You have to give a physics that describes both microscopic and macroscopic domain. So Big Bang can be seen as a union of macro and micro world, where universe largest scale meets the smallest scale. And this point, if we need to explain this, then we need a quantum theory of gravity.
In previous phase, in
Previous.
China, yeah, definitely. In Chinese word, the kind of things represent tanyo, or how can you explain the tanyo? Yeah, it himself or herself, even the tanyo.
So it's the equivalent, the Chinese equivalent to Ouroboros.
Similar things.
Similar.
Tanyo. I'm sorry. Yeah, I cannot explain in English.
Or maybe creating.
Okay, so we established that we need a quantum theory of gravity to explain cosmology predictions like Big Bang. So that is why this area called cosmology and string theory is important, because you see that cosmology constrained string theory. We know string theory lives in 10 dimensions. And if you need to make a connection with 4 dimensions, cosmology can help us constrain those compactifications, right? And similarly, in cosmology, we have a lot of degeneracy that can be constructed from string theory, because string theory gives us insight about what should be your effective field theory in presence of gravity that has UV imprint, right? So together, they can help us unlock the cosmic mystery in a sense. Okay, so what is the dilemma in cosmology? So I would say experimental dilemma is we have 2 different measurements giving rise to 2 different Hubble constants. So supernova will say that the measurement for Hubble constant is between 73 to 74, whereas SIMB measurements predict Hubble constant to be around 67 to 68. So this is called Hubble tension. Then when it comes to theoretical interpretation in cosmology, we have 2 any inflation models that predicts same scalar key parameters like scalar to tensor ratio or spectral index. How can we break these degeneracy or the dilemma? We need more complex inflation model or maybe more good experiments. So since I can't say anything about experiment, for more complex inflation model, one could study higher order corrections in your gravity model. And other thing one could do is add multiple fields, multiple inflation field, and try to study inflation model in those theories.
I mean, what do you mean by complex inflation models?
Complex, it means complex, not like a complex system. It should be complicated system, you would say.
You mean more accurate? In the sense that you include higher correction?
Higher
Or
correction.
you really want to add additional degrees of freedom?
So both. So higher derivative correction will make more accurate, and multiple field theories like adding more degrees of freedom, so that we get more accurate models. Both.
Question?
Yes.
That approach may resolve the second issue you mentioned, like model degeneracy. Like, for example, let's say you have more experiments, so now you have more data, so you can distinguish 2 different degenerate models.
Yes.
That could be possible, but how can you resolve the Hubble tension? Because that means so that those 2 measurements are just measurements, right? And they do not match. So I'm wondering how you can resolve this issue by studying theory. Yeah.
So, okay, so I can't say anything about experiment and how you would say which experiment should I prefer or maybe take more into. What I can say, if my theory is right, then whatever it predicts, it would tell me that which experiments need correction. That much I can say. But I can't say anything how you can improve experiment.
The supernova measurement is essentially the so it's more or less model independent. While the CMB measurement, really, so CMB is really long time ago, that equal to 11, something very old time. But they are predicting from the present expanding the expansion scale, right? So to really connect, it's a strongly model dependent. And the model they are using is a lambda CDM. So by deviating from lambda CDM, that value, 67 to 68, need to change. That's all.
All right. So when I say that we need more improvement in the theory or the models by adding higher curvature, higher order corrections and multi-field inflation models, can we look at cosmology in string theory? Could be one of the thing. But by string theory, I will first say the outline of my talk. So basically, I'll start with what is string theory, because I've been saying that we should study string cosmology in string theory. So I'll just give a short introduction is what is string theory and how string theory changes when we connect it to real world. What are the problems? One of the problem would be swampland versus landscape problem. And then I'll see if we can study cosmology in string theory with the simplest of the example. And I'll see some of the example and then summarize. So what is string theory? So string theory is basically a theory of quantum gravity that unifies quantum mechanics and gravity. It replaces the fundamental particle, which is point particle, with the one-dimensional string. So now everything is described in terms of string. For an anomaly-free theory, we need 10 dimension in string theory. However, we say that extra dimension other than 4 dimension are very small. They are very compact. So maybe in this range of 10 to the power minus 25, since we are too big to see any extra dimension. But if we are very small, in a smaller scale, we would be able to see these extra dimensions. All right. So string theory is unique in 10 dimensions. However, when we try to connect it with 4 dimension, we'll see that there are many 6-dimensional manifold that one can use to reach 4-dimensional string theory or string theory in 4 dimensions. For example, you could start with a string theory in 10 dimension, take a low energy limit, that is get rid of all the massive particles, end up with supergravity in 10 dimension. And now let's try to compactify to 4 dimension. There are many Calabi-Yau manifolds that you can use. For example, if you use torus, it preserves all the supersymmetry you had in 10 dimensions. So you end up with a supergravity theory in 4 dimensions, which has, say, 32 supersymmetry. You could also use Calabi-Yau threefold manifold. It would give you n is equal to 2, which is 8 supersymmetry in 4 dimensions. And you can use Calabi-Yau twofold. That will again break half of the supersymmetry of your original 10-dimensional theory. So from here, you can see, even when we started with a unique theory, in 4 dimensions, we had so many theories with multiple supersymmetry. So uniqueness is broken. Again, the same problem that we had initially in inflation, that there is a degeneracy.
What do you mean by this 32 supersymmetry, 38 supersymmetry?
Number of so basically 8 supercharges in 4 dimensions will give you number of 32 supersymmetry. So your supercharges are 32. So Q is, for example, if Q is the generator and there is Qi, which basically gives you the R symmetry, then this N will give you the number of I's, number of supercharges you have in your 4-dimensional theory. So now, when we compactify in 4 dimensions, we end up with multiple theories. Other problem is that the compactification gives us multiple massless scalar fields corresponding to the moduli of Calabi-Yau manifold. Since they are massless, and we know that in 4 dimension we don't have that many massless fields, we need to give them potential so that they can live in a minima and gain some mass. The one way to do it is moduli stabilization. This mechanism is called moduli stabilization, where we put some fluxes in your 10-dimensional theory and then compactify it. Or you can give some gauge to your 4-dimensional theory as well. So this picture here, it tells you how you can get a potential in your 4-dimensional theory. So either you compactify your 10-dimensional or 11-dimensional theory in presence of flux, or you can just compactify without any flux, end up with a massless theory with massless fields, and then gauge. Give some gauge so that they gain some potential and they find a minima to live in. So this basic idea of adding fluxes will break supersymmetry. So for example, you started with this theory, right? You start with type 2b, compactify in Calabi-Yau 3 and end up with n is equal to 2 supersymmetry. Once you add flux, this n is equal to 2 will be broken to n is equal to 1. All right. So less number of supersymmetry, which is good because we know that in 4 dimension we don't have supersymmetry, right? So breaking is not a problem. The only problem with breaking supersymmetry is that we lose our control over our theory. So the more supersymmetry we have or more symmetry we have, it's easier to manipulate calculation.
We know that supersymmetry is broken.
Yeah, but we also want to control our theory. So we delay the process of breaking supersymmetry as much as we can.
Actually, if you have some information about the supersymmetry breaking, so if you find a correlation among the supersymmetry breaking and the original theory, eventually you hope that when you measure the masses of superparticles, you
Yes.
can get the information.
So the problem is
Yeah.
there is not unique way of breaking
Yeah,
supersymmetry, right? So that is another problem that there is not unique way of breaking supersymmetry. We can add fluxes, and which Calabi-Yau you start with adding fluxes will change the metal content in your 4-dimensional theory, and then everything changes. So your vacua is completely degenerate, that we don't know what vacua will live in. And that is why we say that once you do that, once you compactify string theory to 4 dimension, stabilize the moduli, end up with some potential. So this is the potential you'll get if you do this moduli stabilization. And here this K is called Calvin potential. It's not a potential, it's just a scalar term which depends on moduli fields. And then this is also called W, which is superpotential. They have some properties. One is real, one is Hermitian. Some properties they follow, but they are not unique. So due to complexities in superstring theory, we have to make a lot of assumption what these W and K should be. And since there are a lot of assumptions, we cannot make reliable predictions in this thing, right? In 4 dimension or connected with cosmology.
Sorry.
Yeah.
Is this potential,
Sorry.
is it a potential that one can choose, or it's just like this?
This is it. What you can choose is what this K would be, what this W would be, right? And this K and W, they are function of your moduli fields, like axion and dilaton in one case. But we don't know what this K and what this W is, right? The function, this functional form of these fields.
You also have like INJ, the range of INJ depends on how many much like.
Yeah, we'll come to that. And also one more point to note that this term, which is like a covariant derivative of W, this goes to 0 if you have any supersymmetry in your theory. So that would say if you have a supersymmetry in your theory, this first term will go to 0, right? And you end up with V, which is negative. So this suggests, in string theory, it suggests that you cannot have a supersymmetric de-Sitter vacua. So if you have any supersymmetry in your theory, you will not have de-Sitter vacua, which is consistent because we don't have any supersymmetry in 4 dimension and we know that we have a de-Sitter vacua. So it's consistent, still consistent. Now next, so what we saw is top to bottom approach, where we saw that we can start with the fundamental string theory, try to derive a observer, which is in 4 dimension. But we saw that it depends on internal compact manifold and also the supersymmetry breaking mechanism, which in the sense, we can say that string theory predicts 10 to the power 500 possible vacua if you start with unique theory and you come to 4 dimension, right? It doesn't give anything if we do the top to bottom approach. So let's start with bottom to top, which would be start with standard model, see what you get from cosmology observations, and then try to fit it into the string theory framework. Like the basic things that is string theory follow, maybe try to include that in your theory. But the question is, can our universe be embedded in string theory? Is it even possible to have a effective field theory that has gravity, that has something to do with string theory? Okay? So in other way, you can ask the question, can all the consistent low energy effective field theory that include gravity will arise from string theory? So what I'm asking is, if I start with an effective field theory, try to incorporate gravity, is it possible if the theory is consistent? There is an effective field theory, there is gravity, theory itself is consistent. Is it possible that it will definitely be connected to string theory?
What is the definition of consistent?
There is no like divergence. Say, okay. Because the space will, it is an effective field theory, so there is a cutoff scale, but within that cutoff scale, there is no divergence. That would be a consistent theory of gravity.
And so since it is an effective field theory, you have many of them.
Yes.
You have some effective couplings.
Exactly. Yeah.
So the idea is that there may be some ranges of these couplings that cannot come from string theory. This is the idea.
The question is
The
it?
question if
Yeah.
it's possible.
Yeah. So that's the question. Is it possible that there will be some coupling that has no relation with string theory? And the answer is no. So basically, it's not true that you write any effective field theory which is consistent with gravity. It's not true that they will be connected to string theory. So it is possible that you have an effective field theory with gravity which is consistent, but their coupling has no relation with string theory. Okay. So how do we distinguish this good QFT, which is basically part of string landscape? So landscape would be that 10 to the power 500 vacua that would come in the string landscape. So how do we distinguish this good QFT that is part of that landscape from the bad QFT that is part of some swampland? So theories, effective field theories, which are consistent with gravity, but do not come from string theory are called, they belong to swampland. So this is swampland. Lot of effective field theory you can write, and but only few, which is 10 to the power 500, will belong to quantum gravity, and you don't know how to distinguish.
So just a comment that, some people like to say, rather than consistent with a consistent theory that can arise from string theory, but can arise from any quantum gravity theory. So people, it might be a kind of political thing that people like to say that,
So
but
you
some
identify
people-
quantum gravity with string theory automatically. But
Well,
you say
some people
can be
don't
wider.
want to do that.
Yes.
Can be wider.
So
But what you're saying is that 10 to the 500 is more. In the swampland.
in swampland there are too many. We don't know. There you could have many.
Because I just learned that 10 to the 500 is a small number, so that's why I wanted to inquire.
Yeah, compared to this, so 10 to the power 500 is here, and just look at the swampland area, right? So if it is relative, then we can say that small number. It's all about relative. Right? So
But we don't know, we have no idea how many are there.
this 10 to the power 5, in swampland?
Right.
Yeah, we don't.
I thought the 10 to the 500 was also just an estimate. So-
Yeah, it's an estimate.
And even if you include F theory, it's like even vastly bigger than that, like 10 to 200,000 or something.
But wait,
Um,
you can
but-
suppose almost all of them, right? Because just not just our universe.
Yes.
Some of them has n equal a supersymmetry. We surely know that we cannot describe our universe.
No. So basically, in landscape, I'm saying when we break every supersymmetry and everything, then there are these many. So when you have n is equal to 8, there are fewer. It's not 10 to the power 500 theory with n is equal to 8 supersymmetry. So this 10 to the power 500 theories are when you have broken all the supersymmetry and everything. Then it becomes this big.
I just want to say that the problem we have is not just we have too many solutions that can possibly explain our universe. Actually, we do not, right? I mean,
Yeah, we do not.
almost all of them fit in our.
Yes. Agree. Agree. Because I said that in landscape, we will have theory which has ADS vector. We know that it will not describe our universe, right? So even in the landscape, we can have theories that has no relation with our real world. But there are theories for sure which are related to. And how will we get it? In string theory and cosmology, we have to work together to.
You know, in particle physics, there is one concept that is used, which is kind of heuristic. It's not very well defined, and some people don't like it, which is naturalness. In other words, you have a parameter space, all parameters are okay, but some models are more natural than others because some models have less cancellation. All these models have the same naturalness.
Oh, I don't know about the naturalness. In string theory, we don't talk about fine tuning and naturalness.
You don't have kind of any. So what I mean is that you cannot use the same concept. For instance, people discuss, think about axial physics, for instance. They introduce the axiom because they want to explain why you have a cancellation, very large cancellation of the CP breaking, breaking, and so on. But actually, this is not really a prediction. If nature decides like that, you are out of luck. And so, and the same is about the prediction of supersymmetry, low energy supersymmetry. We should have a naturalness. So in this case, it's not all the models are equally, let's say, natural.
Yes.
You don't care. You don't have any way to make a kind of hierarchy.
No.
She just classified the field theory as a landscape and a swampland. But let's say, I guess, to rephrase the question differently, where does our standard model belong? Does it belong to landscape? One of the 18 parameters model is one of the example of the landscape, or just
that's the hope
so
that it belongs to.
No, but because for example, one of the issue of there is no symmetry that is protecting the correction to the Higgs boson is unstable on the quantum and so you do not really. People say the most natural value of the Higgs boson mass should be the gut scale or the Planck scale.
Planck scales.
And instead it's not. So here there is no way to use this guy. It was just curiosity.
Yes. So I think, if I could say that in string theory, instead of depending on any fine tuning or naturalness, we only just rely on mathematical consistency. That it should be mathematically consistent theory, and then we'll see what happens about naturalness and everything. Everything is allowed as long as there is no mathematical inconsistency. So how do we distinguish? The program is called swampland program. I prefer it should be called landscape program, because we are looking at what theories belongs to landscape. But it's called swampland program. It answers at low energy, what is the UV imprint of quantum gravity left? So based on what string theory allows, we have some criteria or some rules that we want our effective theory, which belongs to landscape, should follow. So some of the rules are this, and they are not over. They're still under work. So people are still, every day there are some rules or maybe redefining these rules. But 2 rules that are fixed, 2 or 3 rules that are fixed is this: no global symmetry. So we cannot have a global symmetry in quantum gravity, and we cannot have gravity conjecture, it says that the gravity force has to be the weakest force in your nature. So these 2 are consistent because they are demanded from the black holes. So black hole says that you cannot have a global symmetry because it will not conserve if you have a global symmetry, you will have a conserved charge, And if you have a black hole in your theory, it will not conserve this charge after radiation. So you
These
cannot.
properties are low, the effective theory, the low theory.
Yes.
low energy.
So this property, every effective field theory that comes from a string theory should follow. So mass of a particle should always be less than charge of particle. This again from the black hole physics. Then there is distance conjecture and DS conjecture. These are the two conjectures that we will
So
focus on.
does it mean that it does not allow any neutral particle?
Neutral particle is fine.
Because
wait.
charge is zero.
No. Charge is zero. Neutral particle would mean that if you keep adding, so black hole mass should be greater than black hole charge, right? So if you keep on adding massive particle, that still remains true, right? If you have a neutral particle, you're adding zero charge, but you're adding massive particle. So this m greater than q for black hole remains true. So you can have neutral particle, but you cannot have a particle where the charge is less than mass. Otherwise, what will happen at one point, the mass of black hole will become less than charge.
So you cannot have a massless charge particle.
Massless charge particle, no.
That's less charge of particle. It does not break any equal.
So massless charge particle.
So yes,
M less than
zero spread, yeah, massless charge particle is fine. Okay. Should I move? All right, so let's see. Okay.
Why I know many particles that are longer than Q, I don't know. Neutral particle. Yeah, in which units? How do you?
They're in unit where m and q has same
Yeah.
the natural units, which we say c is equal to 1, h is equal to 1. So distance conjecture is something that tells you the range of your effective field, such that where your effective field is valid, till what range of your this field distance your effective field is valid. And then there is DS conjecture, which puts restriction on the minimum value of your potential. If your potential you say is positive, which is de Sitter solution, then your minimum, how flat it can get, or if there is a minima or extrema. So this DS conjecture will talk about that. Okay, let's see the distance conjecture. So in field theory, if you have pure quantum field theory with no gravity, then all the values of phi is allowed. It can take negative value, it can take positive infinite value, all the values are allowed in quantum field theory. The moment you include gravity, it introduces a scale. Why? Because as you move away from the center, so for example, at center, you have mass of your particle is mp. As you move away from your center, maybe the moduli space, at q, the mass particles you'll get at the boundary of your effective field theory will be lighter and lighter. So at some range, when this del phi goes to infinity, you'll end up with infinite towers of massless black hole. And that is where your effective field theory will break down. Because you cannot have effective field theory with infinite towers of massless states. Right? You cannot have infinite number of degrees of freedom in effective field theory. So this del phi should be less than this Planck mass of order 1. So this is some restriction that is putting in your effective field theory because of the presence of gravity. Okay, and then the next is DS conjecture, that is distance conjecture. This is DS conjecture. This tells you if you have a positive potential that comes from that is consistent with UV theory, then you should follow either this or this. So see, this is a conjecture that was given by these people in 2018 and then redefined to add this extra condition in 2019. So this condition tells you that your slope has to be greater than or equal to the potential value, where C is a positive constant of order 1. So if you look at this thing, if you have a this thing, say minima, where the gradient is 0, this tells you that only allowed potential is either negative or 0, right? So for a minima, for your theory to have a minima, the only potential that is allowed is ADS or flat. So there is no DS allowed according to string theory here. And then again, the redefined conjecture says, okay, say if this condition is not followed, if you have a minima, then it has to be an unstable minima. You cannot have a stable de Sitter in your theory that comes from string theory. That is the DS conjecture proposed by these people. So the first condition tells us that potential cannot be too flat and it has to be steep one. And second condition is telling us that potential must be unstable. If you have a de Sitter, then it has to be unstable. But we know that there are examples like KKLT, where they have constructed a metastable de Sitter solution. The difference is these conjectures are coming from top to bottom approach. And the KKLT was constructed from bottom to top. So they started with 4-dimensional theory. They said that, okay, we will have some string knowledge and we will construct a de Sitter. So there is a debate. There's a debate going on between two set of scientists. So one scientists who are proposing de Sitter conjecture, they are saying that you cannot have a stable or metastable de Sitter vacua coming from string theory. And whatever you constructed, saying KKLT, which is a metastable de Sitter solution, that must belong to a swampland. It has nothing to do with string theory. It doesn't belong to landscape. Whereas KKLT people, group of people who are following KKLT, they are saying that you need to improve your conjecture. There is something wrong here. So we don't know what to follow from string theory. We don't know if we should follow this conjecture or if we should just say that, okay, we have some de-stable solution coming from string theory. Because this conjecture is not concrete. So we can still say that since we know that in observable universe, we have de Sitter vacua, which is metastable, then string theory definitely should allow for a metastable de Sitter vacua. However, if we say that this conjecture, say distance conjecture is followed, then the slow roll inflation and large field inflations are in conflict with string theory. Okay. And what is consistent with swampland conjecture? Basically, theories that are consistent with inflation theory that are consistent with any effective field theory that would come from string theory would be inflation theory where you have included Gauss-Bonnet correction, inflation theory where you have, say, some temperature, and also inflation theory where you have multiple fields. So these are three models. There are other models as well, but these are three models that are consistent with string theory, swampland conjecture. Now, knowing this, this is basically how they address the puzzle in multi-field. So basically, they are saying that you can still have slow roll without breaking your potential condition, because the turn that this extra field gives will reduce your potential range, allowing you to have slow roll and this potential to be less than what de Sitter conjecture is demanding. Knowing this, we want to study string gravity in 4 dimensions. Basically, we want to study inflation models in 4 dimensions. So if you compactify string theory, heterotic string theory to 4 dimensions, in low energy limit, you end up with this action. So this action has two fields. One is dilaton and the psi is like an axion field. And for 4 derivative action, if you just cut off at 4 derivative, you will end up with a Gauss-Bonnet correction and also a Chern-Simons correction. And this coupling, which is called Gauss-Bonnet coupling in 4 dimensions, it cannot be a constant because then it will be a topological term and not contributing to any dynamics. This coupling depends on some scalar field and that will be fixed depending on which heterotic you choose, right? Which string theory you choose and which compactification you choose, this coupling will be fixed. Now, the presence of axion field in this thing is given as this. So there is psi r tilde. This is the Chern-Simons term. Psi is axion field and this r tilde is basically dual of Riemann tensor. Now, usually people just study Gauss-Bonnet correction or multi-field correction, right? But what we are saying from string theory in 4 dimension, you cannot get rid of axion field. It has to belong to gravitational sector, and it comes from the curvature terms in string theory, right? So we should consider this model where you have a Gauss-Bonnet correction and also a axion field. So looking at this model, we've been,
That model is kind of belonging to the landscape.
yes, it belongs to landscape because this is following the top bottom approach. So we started with string theory and then we never left string theory. So the moment we'll choose, since if you look at this action number 4, you see that there is no potential, right? The moment it can jump from landscape to swampland is how we break our supersymmetry. So there is some symmetry maybe, and we have to introduce potential. And if we choose wrong potential, then we can jump from landscape to swampland.
Another aspect is that the Chern-Simon, the dynamical Chern-Simon term, and the Gauss-Bonnet is that should be turned on together.
They are turned
One
on together.
cannot turn only Gauss-Bonnet. If I turn off Gauss-Bonnet, then if I turn off this, let's say, dynamical Chern-Simon term, automatically Gauss-Bonnet term also seems to be vanishing because alpha prime is multiplied to both terms.
F is the function F.
Whatever f is, alpha prime should be non-zero, right, to have that, but that also make, so I cannot turn off, there is no theory without Chern-Simon term, once we have a Gauss.
Because this function F is a generic function.
Right.
It's not a generic function.
Yeah,
It will be
it is a
fixed
restriction.
depending on what compactive, the 6-dimensional manifold you choose. This will be uniquely determined.
Yeah, but in general, so if we do not know, so if we want to have a bottom up for this F,
It can be anything.
because
Yeah,
any function includes a zero function.
Yeah.
Also, zero is a function.
Yeah, but I mean, the question is very simple. Having only Gauss-Bonnet and not without any Chern-Simon term,
Yes.
is it belonging to landscape or not? Because you are not allowing that possibility.
Yeah, according to that.
Yeah.
So
No, maybe there's a couple in front.
if you
Or
want, so if you turn off, I'm just guessing, so I could be wrong. Since this, I just started with string theory and came to 4 dimension. And if I exclude any of the term, maybe even axion kinetic term also, I should be in somewhere else.
yeah,
or maybe-
so I will be happy if you have stuff like a f function in front of Gauss-Bonnet. If we have some other function, let's say G, which is function of scalar field and the fermion, then I will be happy because then I can handle independently.
But okay, so you can, if I say one way to think is LGB. When I say LGB, it only has curvature term, right?
Right.
So I could also write, instead of LDCS, I could write LCS, which is Lagrangians of Chern-Simon term, where I would say that R and R tilde is my Chern-Simon Lagrangian, and psi I could put in G, right? G is my function of some axion field here. This also, yeah, this field, this. So this I could write in way like G psi, G a function of some phi and psi, and then this is just the Lagrangian coming from Chern-Simon term. And then you can if you turn off axion, you can get rid of this Chern-Simon term. But one issue with this is that the Chern-Simon term, once you start calculating the equation of motion, in the background of FRW, they do not contribute. So they are effective when you're doing some black hole calculation or gravitational wave calculation. Then you should consider, like I think Ansuk is studying this effect of Chern-Simon term. But if you are Yes.
Potential term is included, different from previous page. Yeah, in this page, there is no potential. but the
Yes,
next page,
I think
Yeah, yes.
I think I,
Potential, you include the potential.
okay, I think I left one equation that I should have included, which would say this plus V, which is function of phi and psi. And that depends on what I choose.
So when considering the cosmology, so usually we put the potential by hand.
By hand, that is true. Yes, here also I'm,
Repeat again, where does it,
Then
sorry?
so where is the potential coming from? Can you repeat this?
Yeah, I will repeat. So basically, potential in string theory should come from moduli stabilization. But we know that the moduli stabilization process is not unique. I'm going to put potential by hand, motivated from string theory and also allowed by cosmology.
So I just have a question when the transistor. So is this like a universal thing you get at 4D of this form, or does it depend on whether
In
it's like
4D, this is the form.
right?
If you
it
start with
doesn't-
heterotic string theory and compactifying Calabi-Yau 3.
Right, I was gonna ask what about 2D, like type 2D for example. Maybe you get different terms.
Yeah, it's possible that there will be a different channel.
So here, what is the criteria for a theory to belong as swampland or string?
This, till this point, this theory, equation number 4 belongs to landscape. Because it's coming from string theory. I haven't used anything that would keep it away. Right? The only way it would go away from landscape is when I introduce a potential. That potential can take it out from landscape, right? We saw that there is a DS conjecture that string theory that is coming from string theory should satisfy.
Yeah.
If I choose a potential that doesn't satisfy that conjecture, then I'm taking it out of landscape.
Okay.
This means that the potential must be different from zero.
Yeah.
So zero potential automatically swampland. Oh, I don't understand. So
No, zero potential is allowed.
it's
Is
allowed,
allowed.
but is not allowed with the conjecture.
Zero potential is allowed. So basically, what is not allowed with conjecture? Conjecture itself is problematic, right? So this is the conjecture, right?
Yeah.
Zero potential is
Zero
allowed.
equals
That's
zero.
your minima. You
So
can have a
equal
zero
to
potential.
zero is okay.
Yeah, trivially satisfying.
Trivially said,
Inequal.
you will have a minima. For zero potential, you're always in the minima.
But the thing here is that this potential is kind of, this criteria is for the minimal setup, right?
Yes.
But if you are starting from such a modified stuff, then your definition of potential is completely different because these additional interactions, Gauss-Bonnet and Chern-Simon, they contribute as an effective potential.
That is why this conjecture is debatable. That is the
Exactly,
debate.
right?
Yeah, but it depends on the people who are working. They say that no, it should not, because we follow everything string theory should follow. So this conjecture should be satisfied. But they still keep on modifying the conjecture. So we'll not say that this is the last conjecture they'll end up with. Maybe they will modify the conjecture such that the metastable de Sitter solutions are allowed. Here they are saying that your potential should be unstable or steep. You cannot have a flat potential. That is why I said that you cannot have slow roll inflation. But if you can have a slow roll inflation if you allow Gauss-Bonnet correction.
Right.
Then you can have slow roll inflation.
And also,
Yes.
question is conjecture.
Mhm.
It's very fancy. I mean, could it be think this kind of thing as the assumption? Under the assumption number 1, under the assumption number 2, under the assumption number 3, you would consider something cosmology. They all are mathematically proved. Conjecture.
If it is a
There are a lot
conjecture.
of conjecture.
It's not it cannot be mathematically proven. It's consistent with some examples they took, but they can't take every example, right? So that's why it's conjecture.
Simply it could be the assumption. Assumption 1, assumption 2, or assumption 3.
Mm.
When starting, I mean that you will start the cosmology. Other things could be the old assumption.
But they start with string theory, not cosmology. So
Yeah, I mean that you put even the potential by hand,
yeah.
not come from the string theory.
That's-
But for the cosmology, you need to put the potential by hand.
Yeah. Here also I'm putting by hand only. Okay, so what we have learned. So what we learned. Oops, am I doing something? Is that if you have a Gauss-Bonnet inflation, they say that it is only consistent with swampland conjecture when your coupling, this Gauss-Bonnet coupling, it should be F5. So when your Gauss-Bonnet coupling and your potential has this sort of relation, they should be inversely proportional to each other, right? So we know, so what I am going to say that this is the takeaway message is that we know what Gauss-Bonnet coupling should be from string theory. And we know that a swampland criteria could be satisfied, and it has been satisfied if your coupling and potential has this sort of relation. So let's take the coupling from string theory and try to build potential such that this condition is satisfied, right?
If you
One more constraint you
that kind of coupling function, then a lot
sorry.
of calculation could be simpler.
Sorry, can you repeat?
Under that the coupling function, psi phi is something different.
Yes.
Potential, then a lot of calculation could be simplified.
Exactly.
So
And we know that this coupling function is sort of unique coming from the compactification. Then it puts some restriction on what potential you're going to choose, right? That there is extra condition. Initially you could have chosen all the potential, but now there is one more restriction coming from the Gauss-Bonnet coupling. So this allows for steep potential, and you will have a consistent theory, inflation theory that is consistent with swampland criteria. Multi-field inflation, have I moved? Okay, multi-field inflation we already saw that how it satisfies and here. Okay, so this is the equation of motions for the action that I wrote. If I add a potential and I am allowing my potential to have to be a function of phi and psi both. I could also choose a potential which is just function of phi, right? Since I know in weak coupling limit, this coupling is only function of dilaton. It's not a function of axion. So I could also restrict my potential to be just function of phi. But right now I'm just allowing it to be function of phi and psi. That is why I have this and this term both. And this is equation of motion for metric. And this term, this extra blue term, they are coming because in presence of Gauss-Bonnet, and Chern-Simon term is not contributing here.
What was the B parameter in previous page B? Because that seems to be the
This B parameter was 1.
where does
So
the B
this
parameter-
2B
Ah,
phi.
2B5.
B is 1 here.
Okay, I see. That's the coupling, the phi and the psi.
Yes.
Okay.
That gives the weight of how your axion and dilaton are coupled. So, okay, so I just mentioned that the contribution to the equation of motion from Chern-Simon term vanishes in for FRW metric. They do not contribute to cosmological part of equations, but they will contribute if you have energy momentum or tensor and you're using anything related to that. Now, given that you have a coupling, you can define something called effective potential that relates your coupling and your potential. And we have this relation that's studied in this paper. This is the relation for effective potential. And instead of putting constraint on potential, we will be putting this ds constraint on effective potential. Yes.
Time is derivative with respect to what?
Phi with respect to fields. So we have two fields, phi with this prime you're asking.
Yes, yes.
So this is basically, you can, it's with respect to phi and psi. Right?
Then the
What is accept?
two terms.
Two fields. We have two fields, right? We have phi field and we have psi, axion and dilaton. Two fields.
Phi and psi, what is chi?
Oh, it should be this psi. So basically, yeah, because of action, I want to simplify my action such that it's just kinetic term. So there is some overall factor in psi, some constant this thing, but So basically, if you take this is two equation, right? Equation number 9 is two equation.
I see.
So once when you take derivative with respect to phi, so this is t phi, and then other is derivative with respect to the sky, then this is all. So there are two equations because f also depends on phi and chi in general. So this is the effective potential you can write, and then this is something that I am interested in, but it's very complicated coupling function. This coupling was studied for for black hole calculation, and they found very good results. For this coupling, they show that the supergravity calculation matches with string theory calculation. But the problem is, which we are working on, I'm working with Gansuk and Sokte, and we are finding it difficult to actually solve this for equation of motion because the function is too complicated. But we can take some limit, which we do. We take weak gravity limit where this coupling function, this complicated coupling function approaches just this. So it just depends on dilatant field. It does not depend on axion at all. And for this, we work on some potential. So this is the natural potential. And we'll use this potential. And if you see, this is the plot for potential, and this one is plot for effective potential. So effective potential is a potential where you have potential plus coupling, something that new that we have defined.
So in ordinary natural equation, one question though, only the last term. Do you introduce the second term?
Because we have two field, right?
Yeah, in a
Because
single
we,
field.
we want that potential to be function of dilaton and axion both. So this is why we added this term. And this will be the effective potential. So this should be the action that I should have written, which has some potential here. And for weak coupling limit, we calculated all this thing.
And sorry, does that extra term you added, does it have an origin in string theory, or you added that, or how does it come about?
Oh, this thing is not originated from string theory. It is something that you have to use this moduli stabilization process that I said, which introduces potential. This will come when you do the moduli stabilization in string theory. After you have reached 4-dimension compactification, then you do moduli stabilization, which is not unique.
I mean, is it like a D-term potential or F-term potential, or?
It could be both.
Okay.
Right, because it depends on what manifold you choose. You could have scalar moduli as well as complex structure moduli, and depending on what moduli you have, you can have F term and D term.
Right, and that's typically the form you would get in those
Yeah,
cases.
in the potential that I wrote, this K and W, that will be.
Okay.
Yeah, so this is thing, and then the same thing we followed.
But here phi and the psi both are real fields.
Yeah, real field, real.
In the F term, there's a complex scalar field, isn't it? Or in the D term, D term and the F term potential, especially F term, the scalars are complex.
Here also, so complex state, so basically when you'll write, you'll make it real. You'll only real part will contribute. So for example, this, okay, I think I opened it. So when we do this compactification, you have this called complex structure moduli, which is function of dilaton and axion as a complex
As a
field.
combination, they
become real. Yes. So basically this K is like giving the kinetic term for this tau. So tau is like phi plus I psi. And then when you write, you'll just end up with real fields in the. Okay, now you have effective potential. For weak field, we have this term. So this is the potential, effective potential. Sorry, this is just potential. This is the effective potential in this form. And the effective potential can also be written as this form. You'll see that this is how the field will follow. So we still trying to find what should be the correct potential, because once you include multi-field as well as Gauss-Bonnet, the perturbation calculation gets out of hand, which Gansuk would agree to, because I am very new to cosmology, so I don't know how to do this perturbation calculation. I'm relying on them, and I only know what motivation should be for Gauss-Bonnet coupling. So it turns out that the perturbation calculation gets out of hand once you add Gauss-Bonnet coupling. And then if you don't know how to do the perturbation calculation, you don't know how to calculate spectral index and this thing. So we don't have a observation or key parameters that you observe, but something we have here. Maybe in some other talk, I'll present what the result I have.
So in the previous picture, roughly could you? So I mean, I'd like to understand the effect of the the extra scalars that couple to the Chern-Simon dynamical Chern-Simon term. So beta parameter, if it is a zero, it's a single field inflation potential, right?
If what? Sorry.
If beta equal to zero,
Yes.
then how does the potential the graph look like? I'd like to see how the psi term actually changes the shape of the potential.
So, okay, so this beta is basically cos psi, right? So it's adding the periodicity in your potential.
Beta is the
So basically this term which is coming from the axion, it's a cos psi term. So if I put, say, you're saying that if I put beta to 0,
yes.
you don't want the effect of periodicity, right? So then it instead of this periodicity, you just have one line.
But then I am given only one.
One, yeah. You don't have the periodicity because of, so the periodicity is coming because of this cos psi, right? Okay, so let me summarize. So we studied that string theory is defined in 10 dimensions and a compactification process become necessary to ensure its compatibility with 4 dimensions. Each compactification represents different low energy physics and it generates a landscape of string theory. In recent development of string theory, it has been suggested that not all quantum field theory that are consistent with gravitational theory are related to quantum gravity or string theory. So you should follow some swampland conjecture to study any theory that has to be related to UV sensitive theory, or say. And the take home message that I want to say is that starting from heterotic string theory, compactify on Calabi-Yau 3, you could replace this with any manifold and any string theory because all the string theory are related by some duality. But this is one example. A heterotic string theory, compactify on Calabi-Yau 3, gives the Gauss-Bonnet coupling, which is relatively unique and with some subtlety, but at tree level, it's completely unique and alpha prime correction will give some subtleties there. So starting with heterotic string theory, however, starting with heterotic string theory, compactify on Calabi-Yau manifold, the moduli potential is not entirely unique. And there are various ways to break supersymmetry, and this moduli stabilization is not unique. So we should focus on effective theory with unique Gauss-Bonnet coupling and try to look for a moduli potential that fits the observation. Till now, all the papers that I have read, which consider Gauss-Bonnet coupling or Gauss-Bonnet correction, they say that this is my potential, and since it should be inversely proportional to Gauss-Bonnet coupling, that should be my coupling. I'm saying let's look different way. Let's focus on what is your coupling, which is coming from string theory, and then try to look for the potential that gives the correct observation and that might end up in landscape, right? So thank you. So these are some work that I did recently. So if someone is interested in discussing this, so we with Bamu and with Professor Lee, we did some topological study of Gauss-Bonnet black hole, and then we also constructed some Dilton-Weil multiplet in n is equal to 3 supergravity in 4 dimension, and there is another work coming up where we have constructed a variant of Dilton-Weil multiplets. So these last two papers are something in supergravity, and this other one is in black hole. And although I presented a cosmology work, I don't have a paper in cosmology yet. So hope maybe in 2-3 months. Yeah. Thank you.